Welcome back. We were discussing the diode rectifiers with different loading conditions. In this lecture, we will focus what is the benefit of using the freewheeling diode when the load is having the inductive element in the form of RL load. So again, the source that we are using is basically the single phase source, which is given by Vs equal to Vm sin omega t. It means the maximum voltage is Vm with the frequency omega. Now in this circuit we have the load which is comprising of one resistor and one inductor. The diode D1 is the main diode which is functioning as the rectifier, whereas diode D2 is functioning as the freewheeling diode. We will focus what is the benefit of using this freewheeling diode in the network. So there are two currents. One is the current which is flowing through the diode D1, which is the main current originating from the source. And there is one more current, the current which is flowing through diode D2, that is circulating between the load and the diode D2. So there will be two operations, the operation when the source is connected and the operation where the source is disconnected with the help of the switch or the main diode being the reverse biased conditions. So this is when the diode D1 is reverse biased. This is when the diode D1 is under forward biased. So the load RL will come directly in connection with the source when the diode D1 will be forward biased, and there will be no source when the diode is reversed biased. So we can see from this waveform that the output voltage and the output current which is flowing with respect to omega t, we can see that the cycle which are positive for the AC wave or the input are rectified, and there is a continuous flow of the current between 0 to the 2 pi or with respect to time t. The diode D1 is in the conduction from 0 to pi, that is the first half cycle, and then again it becomes on after 2 pi. So here the diode D1 is off state between pi to 2 pi. Whereas on the reverse side, the diode D2 will be on when the diode D1 is basically off. So the off period of the diode D1 is basically the on period of the diode D2. Here the diode D2 is basically off. Then again it will be off, and then here it will be on. So here it is off. So the diode D1 is off and diode D2 is on. The effect of using the freewheeling diode have many perspectives, like it prevents the load voltage from becoming negative. So we can see that the current I0 is continuously flowing even the load voltage is 0. So the current is not becoming negative. Second, the energy which is stored in the inductor transfers to the resistor through the freewheeling diode, so the efficiency of the system is basically improved. The load current is more smooth now, which improves the performance of the overall system. So if the load here is RL in nature for a rectifier, what happened? That let us discuss. So we are having one more DC source which is connected apart from the RL load here. So you can see that we don't require any freewheeling diode here in this particular case. The source is again the single phase source, and there is only one diode which is connected. So there will be two conditions. One is the forward bias condition of diode D1 and the reverse bias condition of the diode D2. Generally what happened here, this is basically known as the zone where the source is connected. So this is a forced response, and here the source is disconnected. So this is basically the natural response or the steady state response. If you see the current and the voltage is basically sinusoidal in nature. So we have the voltage which is varying with respect to time t in the form of a sine wave, and these voltage, DC voltage, which is a constant voltage, we have in the form of VDC. And the conduction period will start from certain alpha, and then it will discontinue up to beta, and we have the first half cycle at pi. So we can say that beta is more than pi. Now what is this beta extinction angle? Let us discuss that. So diode will remain off as long as the voltage of the AC source is less than the DC source. So we have the source voltage and we have one DC source which is connected in the network. If the DC source is more than the source voltage Vs, then the diode will be off. So the diode will be on only when the source voltage will be more than the DC voltage. So here the diode will be on state. Diode will conduct at a certain alpha, which we can find out by equating Vm sin alpha is equal to Vdc. You can see that the waveform Vs is given by Vm sin of omega t. So here instead of omega t, we will be putting alpha. So it is Vm sin alpha, and that has to be equal to the DC voltage. So from this equation, we can find what is alpha, which is equal to sine inverse of Vdc by Vm. The KVL equation in the circuit, if we apply, then it is equal to Vm sin omega t, the voltage drop in the resistor, the voltage drop in the inductor given by Ldi by dt, and this is the DC source. So if we sum all this, will be equal to the source voltage Vs. The total current response, or the current which is flowing in the circuit, is the summation of the forced response and the natural response. Here when the source is connected, and natural response when the source is disconnected. So the forced response solution we have already seen in the previous lecture is, it is Vm by Z sin omega t minus theta minus Vdc by R. Whereas the natural response we have A e to the power minus t by tau, where tau is basically the time constant given by L by R. So these two equations, when we add in the total current response, we get I of omega t, the conduction period from alpha to beta. Beta is basically the extinction angle when there is no current in the circuit. So here we have the total current which is flowing from alpha to beta. The second part of the equation is coming from the natural response, and the first part of the equation is coming from the forced response. Now if we solve for the constant A, which we can obtain when I of alpha is equal to 0, then we get the value of A. So this A expression we can substitute here in the main expression of the current. So the average power which is absorbed by the resistor, then in that case we can obtain as I RMS square into R, which is the fundamental equation. I RMS we can obtain as the root mean square, the square root of the time period, and here we have the square term of the current, the integration coming from alpha to beta, which is the net conduction period. Average power, if we want to calculate for the DC source, which will be equal to the net average current multiplied with the potential or the battery voltage Vdc. So the current I0 is obtained as I omega t integrating from alpha to beta, and the time period is 1 by 2 pi. So the total power which is supplied by the AC source, assuming the diode to be idle and there is no losses in the diode or the inductor, we have the AC component I RMS square plus R, and there is DC component I0 plus Vdc. So whatever the battery we have here, the current is flowing is I0. So I0 and Vdc, this is giving you the DC power, and I RMS square into R will give you the AC power. So this we can also obtain as the product of voltage into current with respect to time t, omega t, integrating from 0 to 2 pi over the time period 1 by 2 pi. However, the conduction is from alpha to beta, because after beta the current will not be there. Hence, we will be having the equation 1 by 2 pi Vm sin omega t, which is basically the source voltage multiplied with the current which is flowing in the network. We get the product as the power, which is the AC power. So this complete the discussion on the rectifiers having the different loading conditions. Let us see the coming lecture. Thank you for now.